right? So what are we talking about? So we already started the lesson. What are we talking about on Thursday, right?
Yes.
What are we talking about?
We were talking about how two sets of data interact with each other.
Yeah, that is what we were talking about. So when we're talking about correlation, first off, that's the overarching theme of the chapter, yeah? But with the correlation analysis, what are we talking about? The techniques to measure, like you said, the relationship between two variables. What are those two variables called? One's called the dependent variable and one's called the independent variable. That's good. Now how do those two relate?
The dependent variable is dependent on the independent
There you
variable.
go. So what we look at is that independent variable. That's the one we're going to change around, right? And whatever happens with that, something's going to happen with the dependent, isn't it? Now that's regression. That's that's later on today, actually.
Fast.
But so far, when we've looked at correlation, what have we looked at? When we're talking about the relationship between those two variables, correlation, right? What have we looked at? So we got the x and y axis, but what does that tell us? It tells us what? The blank and blank. What are the two aspects, the two characteristics of that relationship this correlation tells us about? The what? Huh? Well, no. It tells us what? Let's look at this slide right here. Tells us,
You got a range.
Positive and negative.
right, it tells us the direction, doesn't it, of the relationship. So some of them, remember, let's look at these down here. Some of them are heading what? To the northeast up there, aren't they? Those are positive, aren't they? Because for every time that x goes over, the y goes up one positive, doesn't it? Remember? And these over here are negative, aren't they? Remember, this is the demand curve, isn't it? So for every one that x goes over, that y is going down one, isn't it? Remember? To stay on that line? Okay. Now, what's going on with this, though? So we got these scatter plots, don't we? That's the first thing we did. Remember? And what did we try to do with the scatter plot? We tried to draw a line through this thing, didn't we? And what did we try to do with that line? We could draw one line through it. What's the condition I put on that line that we tried to draw through there?
Went through the most points possible.
That's right. It went through the most points possible, didn't it? Or at very least it got as close to as many points as it could, huh? Of course, being close, if it's right on the point, what's the distance between the point and the line?
It's right on it.
If it's right on it, there's no distance, is there? It's zero. That's going to become important just a little bit, but not just so long as you can conceptualize that, okay? All right, so we got these scatter plots, and I would put the line right here, wouldn't you? I think that would probably be the closest, yeah, to as many dots. But maybe this line has actually less, it's not right on as many dots, but it's still closer to more dots. I don't know. But even if we do have the line, we don't know exactly what that relationship is, do we? It's kind of in the eye of the beholder, right? So what do we have in order to tell us more precisely about that relationship?
We have our correlation scale.
Right, our correlation coefficient. Remember that? Remember this thing right here? So it's that big old nasty formula. I'll show it to you again in a second.
Yeah.
We represent it as R. We solve for the R in that formula. Now, what does that R fall between? 1 and negative 1, doesn't it? Remember that? So it's a coefficient, remember? So it's a scale, isn't it? And every time we solve for that R, it's going to fall between negative 1 and 1. Now, if it falls towards that 1, we're talking about a positive or negative relationship. It's positive, isn't it? I don't see a negative sign there. That's positive. And the closer it gets to 1, these, what? The weaker? The stronger, that's right. That's the word I was looking for. The stronger the relationship. And as we go down this way, towards the negative 1, it gets weaker and weaker, right? No, it doesn't. What's going on as we get towards the negative 1?
Stronger is negative.
It's also getting stronger, but that's a negative relationship, so it's strongly negatively correlated. Remember? The y goes down negative for every 1. Man, you've been replaced. Don't even get the SAG after me. What do they call? What's the union out there that handles all the?
Don't ask me. I will know. I will.
All the. You know what I'm talking about? The union that handles all the film workers, crews, and everything. Don't get them after me, man. All right. So, does everybody know what I'm talking about? Yeah. So if it's going down 1 for every one it moves over, it's negative over here, isn't it? So it's going to give us a negative. But this strong relationship is a strong relationship. Okay? All right, what if it's hovering around 0? Again, it being that number we get when we solve for this big nasty formula I'm about to show you. If it's hovering around 0, what is that telling us about those two variables, the relationship of those two variables?
There's hardly any correlation.
There's no correlation really, right? So it's not going to be right on 0 usually. And we're not usually going to get anything that's right on 1, are we? Or negative 1. Okay? But if it's hovering around here, we can pretty much guess there's no correlation, can't we? Okay? Everybody remember? And that's going to look something like this. It's just a smattering, isn't it? They're all over the place. Right? Okay, correlation coefficient R, this just shows us how to get the averages. So again, we got the x's. Oh yeah, which one goes on the x, the independent or the dependent variable?
Independent.
Independent, x, independent, right? Just like generation X, my generation, completely independent. Your generation, generation Y, completely dependent, right? Isn't that funny? I just thought of that.
I'm technically a millennial still, so.
That is generation Y.
No, it's-
Yeah.
they skipped Y. They went X, millennial, Z.
Right, so millennial is just another name for Y. Let's play some algebra here.
No.
But,
Gen Y is the smart ones. Gen millennials, the not so smart ones.
well, you said they skipped Gen Y. Oh, you're saying they're the same thing, it's just how you call it?
Yeah, how you call it. Gen
Oh,
Y is the
okay.
ones who are actually, kind of smart millennials are the ones that you see on YouTube doing dumb stuff.
Yeah, I'd buy that.
Fair enough.
What about Gen Z?
That's like, well, I don't know.
When were y'all born?
Wait, when did
They're teenagers now?
Gen Y run out?
I'm not sure, I hear different.
No, I thought they
Yes.
said
I thought it
Gen
was
Z was like 95.
Was it 95?
And after?
Yeah, I think so.
So were some of y'all born in
Oh
95?
shit, I'm
I was
Gen
born in
Z.
98.
You're Gen Z?
Yeah, I'm 98.
You were born in 98?
Yeah,
So you're Gen Z? That explains a lot, dude.
for real.
That explains a lot. So yeah, I don't know what the Gen Z, I don't even know what they are. They're not even on this chart. They're like in that no correlation type thing. Just wandering around all over the place with no kind of.
Going to Helen in Florida and
Yeah, that's right. That's right.
doing whatever.
Do whatever they want.
That's right.
Going to Alabama for months on end and no. I'm just- Anywho.
Let's
So-
continue our sales calls.
All right, so again, Y dependent, right? Okay, so when we take the average, so that chart right there is just this chart, isn't it? Just that chart, okay? That's all that is. But it's just showing us how we can chart the averages. So we took the average of all these. Each one of these dots has an X and a Y, doesn't it? Has an X coordinate and a Y coordinate, doesn't it? Remember? Okay, so we can average the Y coordinate here, and we can average the X coordinate here, can't we? Good? Okay. And we are going to use that too, aren't we? That's just a graphical representation of that. But I like that. It's a good illustration. Because it shows you the space between. Right? There's space between all of them, isn't there? But there's still one average, okay? That idea is going to play into our regression idea, okay? And again, all this data just comes from this chart. Remember our copier salespeople? Remember a certain number of calls, and there'll be who is it? The new manager or whatever is trying to make the argument that you make more calls, we're going to make more sales. Yeah, so we've got to find, is that true? Is there a correlation between the number of sales calls made and the number of sales? Okay, that was that example. Okay, but here's that big old nasty formula, remember? And it is bad, isn't it? And why is it bad?
There's too many letters.
There's a lot of letters, but not only that, what's going on up in these letters? So how do you actually write this out if you were doing this long form? You'd have to do this big old chart right here. And this is just for the numerator up here. What about for the denominator down here? What do you have? Standard deviation, don't you?
Yeah, sample standard deviation.
Sample standard deviation. And do you remember that? Doing the big old chart for that one as well? That's another big. So you'd have to do another chart like that for that one. It would be X x bar, x minus x bar squared, add it all up, remember? And then you have to do it again for the y's, wouldn't you? For the y's over here. That would be for the x's, then you'd have to do another one for the y's. And this is 15 data points, isn't it? So how many data points did our Applewood Auto group have?
About 180, right?
180, didn't it? So you'd be doing that 180 times for this, for the numerator, then 180 times for twice for the standard deviations of both your variables. That doesn't sound fun, does it?
No.
Not only that, probably pretty easy to make a mistake doing that at some point, don't you think? That's why we're going to use a, what do they call those things? A computer to do that. Okay, so, does everybody have a computer at their disposal? If you do, please open up Georgia View.
You know what? I think I do right here. Let me go look.
So go to Georgia View. Maybe I should open it up too. Go to Georgia View and open up that file I sent you today. Y'all have it? Okay, and it's called Applewood, isn't it? We're going to enable the editing, and we're going to blow this sucker up.
Hang on, my computer's not computering.
Yeah, these labs have been running slow for the last week or so. I've noticed that too. It's been taking a while to download things. So let me know when y'all have it. Do you have it? What else y'all want to talk about? Little bit of a change of subject. But we got to think about every eventuality, don't we? All right, so in this last example with this, the manager, she sampled how many people? Copier salespeople, do you remember? What was our sample size there?
15.
It was 15, remember that? From North American Copier Sales. Well, let's pretend like North American Copier Sales is actually a really big company, and they have 10 offices in Canada, 20 offices in the United States, and 5 offices in Mexico. All right, and they have 100 salespeople in each of those offices. How many salespeople is that? That's, what I say, 30 times 10, 3,000. 30 times 100 is 3,000, right? Plus 5 times 100 is 500. So 3,500 employees. And our sample was how big? 15. Huh. Yeah, I don't know. I don't know if that sample's going to do it or not. I don't know if that sample's really representative or if we just happen to pick the 15 people, you know, that gave us the answer we wanted or what. So what can we do to test whether that's a fluke or not? Whether what the sample we picked was truly representative or whether it was just by chance. We got a way of doing it.
Increase your sample size.
Well, we could do that, but what's a way to test the sample that we already have? Remember? We all just bombed a big test over it.
Yeah, I guess I don't remember.
That's why we bombed it.
Exactly. So we can test the significance of that sample using that same method that we used with hypothesis testing, can't we? Remember those 6 steps? Okay. So, what does this say? Testing the significance of R. So recall that the manager from North American Copier Sales found an R of 0.865. Remember, that's what that correlation came up to. So could the result be due to sampling error? Remember, the sample way off from our actual mean, yeah? So if it's due to sampling error, what would the case there be? What would the real deal case? So we found a correlation of 0, but for the purposes of this exercise, we would assume that there's no correlation, wouldn't we? And we're going to disprove that, if we can. And if we can disprove that there's no correlation, it means what? That our correlation is not significant. If we disprove that, it means what?
Correlation is significant.
It is significant, isn't it? Okay? So again, remember how we went on and on about the hardest part about these testing problems is these hypothesis testing problems that we were doing is the setup, right? And that's the same way here, okay? Meaning, I know it's a little unnatural. You're like, I just found that there was a correlation here. But that's that sample. That's that particular sample, the two variables within that sample, isn't it? We're talking about, is this sample significant within the population? Okay? So, it's a change of method, but it all ties in, doesn't it? So, remember this, these 6 steps? And again, the setup is the hardest part, isn't it? So even though we just found that correlation within the sample of 0.65, we're saying within the grander scheme of things, is that a fluke that we found that 0.165, or would we expect to find that 0.865? Right? Okay. So our initial hypothesis is going to be what? It's a little different here. So we're talking about that, aren't we? What does that mean? Well, when we're talking about area under the curve, that can be proportion, percentage, or what's the one looking into the future? Not prediction, but probability. Probability. I really couldn't remember that. I wasn't trying to prompt you. All these P words, it gets confusing, doesn't it? Okay, so the hypothesis is the probability is 0 that the correlation in the population is 0. Okay? That's what we're saying. There is no correlation. Yes, we just found it in that sample, but we're taking a step back and we're saying, pretend like we're going to say that there's no correlation in here. Therefore, if we disprove that null hypothesis, that there's no correlation in the population, then we reject it, don't we? And if we reject that null hypothesis, we are going to accept the what? The alternate hypothesis. In this case, the alternate hypothesis is that the P does not equal 0. Therefore, it is significant. Right? So just set them up with the 0 is what I'm telling you to do. Okay, it's not always equal 0. We'll have to look at the direction. You'll get plenty of practice at that. Okay? With your homework and everything, which I need to put on there. I didn't want to do it yet until we went over some Excel, because I knew some of y'all would be drawing all that stuff out by hand. It would take forever. All right, so we stated our problem. Select the level of significance. We'll use 0.05. Okay, what is that called? Another name. What's the letter for our area level of significance? Remember that? Alpha, right? And where's the alpha in this curve? Is this a one-tailed or two-tailed test?
Two-tailed.
Two-tailed. How'd you know that?
Equals.
The equal sign, isn't it? We're not saying greater than or less than. We're just saying it ain't equal to that. So if my alpha is 0.05, how much area is that?
0.25 on each side.
0.025, right?
Or, yeah, 0.05, so 0.25.
Yeah, 2.5%, isn't it? And the rest of this curve is what? If that's 0.025, that's point what? 95%, isn't it? Remember doing this? Thought you'd never have to see it again when I said that test wasn't cumulative. That final, didn't we? Well, guess what? I told you we'd be back, didn't I?
Yeah.
All right.
Yeah, that's kind of where I screwed up last time.
What, right here?
Yeah, where the two-tailed value for my T-score,
Yeah.
I split my T-score.
Wait, what now?
I split the T-score. I was like,
Oh, instead of the
half and half.
alpha?
So, yeah. So I was like, oh, since it's only telling with this side of the two-tailed, then I should do half of what my T-score is. I'm like, nope.
Yeah. Yeah. That's definitely wrong.
That was just a brain fart on my phone.
Well, did you do supplemental? No.
No, probably not.
We didn't do that bad either, so. All right.
At least I still technically passed.
Yeah, you passed.
In this course, it's considered passing, so yeah.
Yeah, no, you did. You did well. You passed. So
70-some.
I got to release y'all's grades too, by the way, but I just, keep getting busy. But I will really. You'll know what you're doing cruising into the final. What you need to do.
Cool.
All right. So we got this, right? Now, what do we have to determine? What are these things right here? What is that called? Your your what?
Critical value.
The critical value, isn't it? Okay, so we got to find that, don't we? Are we going to use the T or the Z?
T.
Why are we gonna use the t?
Because of the sample size.
Yeah, all we have is the sample standard deviation, don't we? We don't have the you gotta look back at the problem, but we don't have the population standard deviation. It wasn't given to us. So we gotta use the next best thing, which is a sample standard deviation. So we're gonna use a t value. So where do we get our critical value? We go to the t table, don't we? Students t table. And we go two-tailed test. And we go 95%, remember, across the top? You with me? Do I need to pull it up? Or no? No? Okay. So, I got 95% across the top at two-tailed. I'm going to pull it up, and the reason is this.
Yeah.
There's something different about it this time.
I mean, it'd be easier if we had a visual, a big visual.
I know, I just don't feel like pulling it up.
Too bad.
Let's go home. Let's go.
That's a great idea.
No.
It's on video, you said it.
Dedication.
I think this video is kind of going to end up like some Hillary emails, you know, there's parts that are going to
Despair. All right. Tables. All right, so students T table down here, right? All right, everybody see that? So, first off, let's look at, I want to show you something here. Let's look at what these slides are telling us. What is our critical value right here? Everybody see that? 2.16 and negative 2.16 because two-tailed test, remember? Oops. Now, we got a two-tailed test, don't we? Our alpha is what?
0.05.
0.05. What was our sample size?
15.
15.
That's
What would normally be our degrees of freedom?
1. No, 14. 14.
14 is what it would be. But what is it this time? Where's our answer fall?
Should be 13, because you get 2.
13. Why are we taking 2 degrees of freedom, or 2 n minus 2 this time? No, because remember, normal two-tailed test, we only take 1, remember? 2 variables. That's why it is. Did everybody hear that? Good call. So there's 2 different variables, aren't they? So one variable is n minus 1 and the other is n minus 1, isn't it? So altogether, we still only have the 1 sample size, but we're representing the variable, the same data in 2 different ways with 2 variables, aren't we? Okay? So we're going to take n minus 2 when we pick the critical value this time, okay? You got me? Everybody understand what I'm talking about here? So our sample size is 15. Where is this? 13, isn't it? 2.16. We good? Okay. Now, why did I do that? Is that another instance? It is. Okay. So, we have our critical value. Now we got to make the decision, don't we? We got to run a T or a Z, which is what we've looked at so far this year. We got to determine whether it falls over outside the critical value or inside the critical value. Remember? Okay. So, which value, what are we going to use? Which formula? T. But, let's look at our T formula right here. Does it look any different? Our test statistic, right? Does it look any different? It does, doesn't it? This is the formula we'll be using to test for the correlation coefficient, okay? To test the significance of the correlation coefficient, okay? So it's a different formula. Yes, you will have it on your formula sheet, okay? And it is plug and play, but just remember to use this one, okay? The other one probably won't be on there because that was the last chapter, okay? This is what we're going to be using now. Everybody see that? What is that letter right there, the first one in the formula? R, isn't it? Correlation coefficient. So we take that into account, don't we? So it makes sense. Times the square root of n minus 2, which is our degrees of freedom. Yeah? Times 1 minus r squared. This is actually called the coefficient of determination, but we'll get to that in a little bit. Okay? All right, is everybody good? We good? All right. So, what is the answer they came up with this time? 6.216. If this is point, what is it? What is this, the critical value to what? 16? Are we positive or negative? Where are we playing over here?
Positive.
And what was my t-value this time?
Way the fluff out there.
Yeah, what is it? 6 what?
6.216.
216. I mean, it's way out here, isn't it? So are we going to reject it? We're going to reject it hard, aren't we? Yeah, because it's all the way out here. It's not even close to the critical value, isn't it? We got a tiny, tiny, tiny p-value, don't we? 0.0001, something crazy. We're rejecting this sucker, aren't we? Okay, so what does that mean, though, that we're rejecting it? So we're rejecting the null hypothesis, which is what?
Equal to.
That there's no correlation, right? The correlation 0. Therefore, we're going to accept the null hypothesis, aren't we? Which is what? That there is correlation. That the correlation does not equal 0.
We're going to accept the alternate.
For the population, huh?
We're going to accept the alternate.
We're going to accept the alternate.
Okay, yeah.
Yeah, we're going to reject the null hypothesis, aren't we?
Yeah.
We're rejecting it big time. See, it's all the way out here, isn't it?
Which I think I might have just heard you wrong. I thought you said accept the null. I'm like, what?
Oh, I might have said it backwards, but we're going to accept the alternate. Right?
Yep, that's correct.
Reject the null. Everybody good? Everybody with me? Okay. So, yes, the correlation in the population is not 0. So we're looking at the population, remember that. We do have that sample, don't we? This is talking about, is that sample representative of the population? Okay? Are we good? All right, what time are we out of here?
About 5:50.
6, nah. 6.
3 minutes?
Starts. Oh, 6. Yes, it is 6. It is 6. Yes, it is 6. My bad. I thought you were being smart. All right. Change the subject. We ready? We got to get on to this today. But we're almost there. All right, change the subject. We ready? Now, regression analysis. With correlation, what we were just looking at, what did that tell us about the relationship between those two variables? Told us the direction and what? What did the coefficient tell us?
Negative.
The strength,
The strength, yeah.
right? Whether it was negative or positive and how strong the correlation was, right? Now, this is going to tell us the precise relationship between the two variables, okay? How's it going to do that? Well, it's going to give us a line, all right? And that line is going to enable us to predict what happens to one variable when a change occurs in the other variable, okay? Namely, we're going to be moving around the x, all right? And we're going to see what happens with the y. Understand what I'm saying? We're going to be moving this one back, the x. I don't have one drawn, but we're going to be moving the x back and forth. Really more that way. And we're going to see what happens to the y. Yeah? Kind of what we've already looked at. But we're going to come up with an equation to represent the actual interaction of those two variables. Okay? So, regression analysis. This is a big deal in statistics too, guys. You got to know this one. This is another big one. All right? So in regression analysis, we estimate one variable based on another variable. The y based on the x, yeah? Could do it the other way around, I guess, but it's not really how it's done. The variable being estimated is the dependent. The variable used to make the estimate or predict the value is the independent variable. So we manipulate the x, see what happens with the y, don't we? Okay. The relationship is linear, so we come up with a one best fitting line. Remember doing that? Drawing the trend line through there? That was the best fit for that data set, okay? And that line represents the interaction of those two variables within that data set, okay? And this is going to allow us to predict what's going to happen to the x value, to the dependent value of a variable when we manipulate the x, okay? It'll make more sense in a second. So the least squared principles. Let me ask you about this. What is that? Okay, now we got is that an earring?
I don't wear 'em.
Not even on a weekend?
Only on Tuesdays.
It's Tuesday, dude.
Oh, shit, I forgot. My bad. I'll bring 'em next week.
All right, let me ask you about this. Okay, let's pretend like we're copier salesmen in here, but instead of this weird formula where one person sells 10 copiers for every 5 calls they make, and the other person sells 7 copiers for every one. Let's say we're guaranteed a sale for every phone call we make. So what would be our ratio? It'd be 1 to 1, wouldn't it? 1 phone call to 1 copier sold. Okay? Let's say our leads are that good that we already know everybody wants 1 copier. Okay? So if I make 1 phone call that day, how many copiers am I going to sell? 1. If I make 2, how many am I going to sell?
2,
2. If I make 3, how many am I going to sell?
3.
And if I make 4, how many am I going to sell? 4. Just pretend like that all lines up. Now, if I were to draw the best fitting line through those variables, where would I draw it?
Straight through.
I'd draw it straight through that line, wouldn't I? Well, let me ask you this. How much space is between this first variable right here, the 1 phone call, and that line? How much space is in between there? Is there any space between there? There's none. It's 0, isn't it?
So it's perfect 45-degree line. But every
What about the second one? Is there any space between that variable and that line, that best fitting line? About the third? About the fourth? No, huh? Okay, so we know all 4 of our variables, there's 0 space in between there. What would the answer be if I added up all that space? And to determine how much space is between that line and those variables? 0. They're right on it, aren't they?
a perfect, strong or not perfect positive.
Right. So, let me ask you, perfect positive correlation, but let me ask you this. Why wouldn't I draw the line here? Why would I not?
Because it's too far away from the dot.
It's too far away from the dots, isn't it? I'm just introducing space there, aren't I? In fact, more and more space as we go, isn't it? Everybody see that? Okay. So that kind of ties into the least squares principle, okay? Now, do we normally have perfectly linear lines like this?
Yeah.
What are they normally going to look like? They're normally going to look like those scatter plots that we've been looking at, huh? Something like that. And we got to figure out where that best fitting line is, don't we? But there is a best fitting line, isn't there? I mean, it might not hit all the dots, but there is one line that we can draw through here that minimizes the space between each variable, right? And the line, and that perfect best fitting line. You see what I mean? And that's our goal. If we minimize the space between each of these variables and the line, what is that telling us? If that distance is minimal, the lowest we can get it, when we add up all the distance between all the variables in the line, what does that tell us? It tells us that that's the closest fitting line, isn't it, to the most variables?
The strongest your line can get.
Right, that's the best fitting line we can draw through there. Does that make sense? Okay, and that's what we're talking about right here with the least square principle. Least squares principle. Got me? So we want to draw, it's not going to hit every single point, is it? But what we want to do is minimize the distance between the points and that line. Okay, and the smaller the distance, the better fitting the line is, isn't it? Again, why would the best fitting line through those dots not be like here?
That was all you dots away over yonder.
Because look at all that distance. That line's not even close, is it? I introduced tons of distance there, didn't I? I want the smallest distance between my y's, okay, but we're doing it vertically, okay? And that line, all right? So what I'm going to do is I'm going to calculate those distances, square them and add them up. And the lowest number wins, okay? Now, why would I square those? What does that squaring thing do? gets rid of what?
Negatives.
Yeah, because the ones on the top of it will be negative, won't they? The ones on the bottom will be positive, okay? But it'll still be a balance in there, but we go ahead and square it, least squares, yeah? Now, which is the only one that would have a 0 in there?
Ones that were right on the line.
Right on the line, yeah? There's 0 distance between the line and the variable, okay? And again, this least squares principle is good because it eliminates judgment, doesn't it? So, where's that best fitting line? Well, depends on the method, depends on how it looks. You know, if we're just drawing one through there, it's kind of random, isn't it? But this gives us a definitive answer. The best fitting line is the one that reduces to the highest degree the space between the variables and that line. Which makes sense, doesn't it? Okay. Now, this is just an illustration of what we just did, kind of. Now, oh no, dang it. We're already on 17, and that's where I wanted to stop today. Not yet. I wanted to stop at after 17,
Oh,
before 18.
You getting me upside.
All right.
What's perfect
Oh, I got 4 minutes, y'all. I'll let you out early today. You get 30 seconds. Maybe. Y hat is the S, so we got this value, this formula right here. What is the formula for a line? Who remembers that? I just want to introduce this and we'll go.
Y equals mx plus b.
Y'all remember that from linear algebra? Y equals mx plus b?
Well,
Y is what? Huh?
Y is your
What's the
output.
same? It's the same thing.
Yeah.
It's the intercept. Well, it's twisted around a little bit, but it's your intercept. Mx. I don't even remember it. M is the slope. No, b is the slope.
Your M is your slope and your b is your y here.
Mx is the slope. B is the y-intercept. That's what it was. Couldn't even remember. Now,
And your x is your input.
yeah. Well, this though has how many inputs?
2.
This has 2 inputs. Well, your Mx is 2 inputs. It's 2, isn't it? Because your x is an input. But anyway, y hat equals a plus bx. You should see a familiar pattern there, shouldn't you? Okay, so y hat is what? The estimated value of y for a selected x. So if we have one line coming through here, and we name an x right here, our y is going to be where? Right on that line, isn't it? Okay? So but it's just an estimation. Why is that? Because this line is the best estimator, best predictor we have. So we want to put it on the line, don't we? Okay? So y hat is the estimated value of your selected x. A is the constant, or the intercept, meaning where this sucker crosses, yeah? If that's your line, where it crosses, remember that? Y-intercept, where it intersects the y. Y-intercept. Okay. B is the slope of the fitted line. What's your old formula for slope? Rise over run, remember that? And the formula is for, and x is the value of the independent variable. So that's what we're going to plug in there to say, hey, where's that y going to fall on the line when we plug this whatever x in there, okay? Now, again, we don't get a definitive y, it's just an estimate based off of that line because that's the best estimate we have. That's why it's the y hat, okay? Now, sometimes, actually most of the time, we're going to have to solve for our slope and our y-intercept, aren't we? And here are the formulas for that. What is this first letter in the actual formula for B?
R.
R, that's our correlation coefficient, times what? Standard deviation of the dependent variable over standard deviation of the independent variable. Okay? So we're going to take that, and we're going to plug it in for B. And then we're going to solve for A down here, which is what? Y bar, average of all your y's, minus B, times average of all your x's. Yeah? Where should the B come from? Right there. So we plug B in here, solve the A, and plug it in there.
So on the B, does that say S1 over S2? Is that what that-
SY over SX.
Oh.
So those are your two different dependent independent variables, right? Hey, guess what though? That's a lot of math, isn't it? I wish there was a way to do it on one of these computers.
Yeah, that blows.
Computer, do a formula. I can't get it to go, just kidding. We have a program for that, don't we? What's it called? Excel. regression in Excel. All right, so, 6 o'clock. That took longer than I thought.
Yep, okay.
So you're not getting out early today. You don't have any time for today.
I got my money's worth.